Okay, friends, let's wrap up this first day of probability with rolling some dice experiments. So we looked at dice before. I think it was in randomness when you saw our son Max dump a whole tin of dice out, and then we organized it into piles based on the numbers that showed. Let's just revisit that and the idea of probability. Now that we kind of have an idea. So here's a question for you. Roll a single fair die once. So what's the chance of getting a 3? Chance, probability, likelihood. What's the chance of getting a 3? Okay, think about it. Get the answer in your head. And chances are you probably said, chances are you probably said the chance is 1 in 6. What I want to look at now is to drive home the point. What does it mean to have a 1 in 6 chance? Let's take a look. So friends, what I've done is I've created a die roller in Microsoft Excel. Pretty straightforward. I just simply create the rand between command 1 through 6. And what that does is it randomly selects a digit between 1 and 6. 1, 2, 3, 4, 5, 6. That's basically all a die is. A die is a 6 random number generator. So every time I press the F9 button, I get a new roll. That just rolled a 5. That just rolled another 2. That just rolled a 3, that just rolled a 6, and that just rolled a 3. So you can see right away what 1 in 6 doesn't necessarily mean. 1 in 6 does not mean if you roll a die 6 times, you will get one of each of the sides. You can see we just rolled it 6 times, and we got, once again, a couple gaps. So what I want to look at now is what does it mean to have a 1 in 6 chance? So I'm going to go ahead and do what we usually do, which is let this thing roll many times. And let's see what we get. Okay, friends, here's a good place to stop as any. The idea was just to get a whole lot of trials of our die rolling. And maybe you noticed something. It was kind of fun to watch this pie chart at the beginning when it was kind of skewed. And then as the first couple hundred rolls went in, these pie slices started to even out, so to speak. Notice that these numbers are not perfectly equal to each other, but they're also not that far off from each other. And you might notice that each one of those percentages is roughly equal to about 1/6. So when somebody says the chance of rolling a 3 on a die is 1 in 6, what it really means is roughly 16% of the time you're going to roll a 3. Now, what doesn't it tell you? It doesn't tell you when it's going to happen. It just tells you over a long period of time, it will happen 16% of the time. It doesn't tell you if you roll the die 6 times, you're going to get a 3. It says if you roll the die a lot, 1/6 of the time, you're going to get a 3. And this is one of the reasons that dice are used, is because they're perfect random number generators. Another way of looking at the exact same data, although I like the pie chart, is a bar chart. And you can see that these bars are roughly the same height as each other. What does that tell you? It tells you that the more you roll this die, the more even these bars become and roughly end up being about 1/6 of the time each. Yeah, right now there's more. Oh, did you see that right there? It's starting to fight. The 18 is starting to lose its stranglehold, and it's starting to correct to 17%. So no matter what of the versions of this graph you like to look at, what you're going to see is over time these stabilizing down to 1/6, 1/6, 1/6, 1/6, 1/6, 1/6. Now the next data set, oh, look at that, the 18 is starting to become 17. Yep, because we started out ahead. Little random clumping of 4s, but now it's beginning to kind of fall back from that random clumping of 4s, which is actually a really cool feature of randomness. What I'd like to do now is look at not a fair die. I want to look now at a weighted die. A weighted die. What's the chance of getting a 3 now? Now, when I say a weighted die, I mean that the die has been skewed in some way. I'm going to roll a 6-sided die in Excel that has been weighted. In other words, it's not fair. Let's take a look. Okay, so now this is going to look just like the previous pie chart. We're going to reflect 1, 2, 3, 4, 5, 6. Still a six-sided die. The die still has 6 faces, although it's been weighted in a certain way. So I'm going to roll it the same way. I'm going to use my F9 button to roll the die. There's 6 rolls right there. Okay. And now I'm going to hold down the F9 button. I'm going to let this thing go ahead and roll, and let's see what happens. All right, there's about 6,000 trials again, and hopefully you're noticing what's going on here. Let's take another look at this thing on the other side of the, oh, there we go, right there. That was a fun little reshuffle. So hopefully you're seeing roughly what's going on with this weighted die. And one of the things I want to ask you in your homework is this. How is that die weighted? How? Not how did I manufacture the die? But when I say weighted, what do you think it means? Let's go back and take a look at that again. So when you look at this pie chart, you can definitely see it looks different than the fair die's pie chart. And also, I think the other look in this case is actually even better. It really stands out here, I believe. So I guess mathematically, what I want you to talk about in the homework is, what is the difference between this die and the fair die? People have been cheating on dice for, it's probably not that hard to believe, for hundreds of years. There's a thing called cooked dice. You may have heard that phrase, maybe not, where you actually take a pair of dice and put them in the oven and lightly cook them so that some of the weight goes into the bottom. And the faces that face up in the oven are more likely, therefore, to land face up. Kind of an interesting little gambling strategy. I don't recommend trying it in Vegas. You'll probably get tossed. But anyway, that's another fun little experiment. But what's still the same is the definition of probability. For example, what's the chance of rolling a 3 on this die? Well, it's about 15%. Not 1 in 6. It's more like 1 in 7. We don't even have to know anything about this die to be able to look at these numbers and go, oh, there's a 28% chance of a 1, there's a 14% chance of a 2, there's a 15%, and so forth and so on. And we can hold down the die and get more and more and more reshufflings of the results until we end up with effectively a 0 margin of error on our results. But if you can look at this pie chart, it's basically stabilized. So what hopefully you're seeing is the general relationship here. It's not moving much. I mean, you can always, if you want to, increase the decimal like we've done in the past to see what's really going on, but it's really not changing all that much. So that's a fun one. It's a 6-sided die with atypical results, which is, I think, what makes it kind of interesting. Let's look at one more experiment. So the last experiment is, I think, more applicable to Vegas, rolling a pair of fair dice. So forget the weighted dice for now. Let's go back to rolling a pair of fair dice, okay? So what's the chance of getting, for example, snake eyes? So snake eyes, if you've ever played craps before, snake eyes means you roll a pair of dice and it lands with the 2 1s up. Okay, I want you to think about this right now. Before we look at any data, what do you think the chance of rolling snake eyes is? Write down an answer. Okay, friends, you've got your estimation of what the chance of snake eyes is. Let's take a look. Okay, now my favorite way of actually doing this experiment is with you all in class. This is one of the things I'm missing right now, is being able to give you all a bunch of dice and have you roll them. I bet you figured out at least the possibilities for what could happen if you roll a pair of dice. One way of looking at it is thinking about the sums. That's the first way I'm going to look at this. If the smallest sum is snake eyes. You can get a 1 and a 1, that's a sum of 2. You could also get a 1 and a 2, and that's a sum of 3. You could also get a sum of 4, 5, 6, all the way up through a sum of 12 if both dice land as 6. So right now, the current roll you see, die number 1 is 2, and die number 2, is 4. The sum of those two is 6. So 2 plus 4 is 6. Let's roll again. Okay, we just got a sum of 4 because it went 1 and 3. Let's roll again just to kind of see how this works. Oh, we just got a 1 and 3 again. That's actually kind of cool. We got the same roll twice in a row. Now we got a 1 and 4. Now we got a 1 and 2. This is actually really cool. There were a whole bunch of random 1 clumps there. 2 and 6, 3 and 3, watch the sums down here, 5, 5, 6, 9, 4, 10, and so forth, and so on, and so forth, and so on. I'm going to let this run like we always do and get us a whole bunch of rolls, and let's see what happens. So, but you know what? I think we can see what's going on here pretty well. And you know what? I'm not entirely sure that this pie chart is the best way of looking at this data. It's pretty clear that these are not happening with equal frequency, and we'll get to that in a second. Let's take a look. That might be a better way of looking at it. So what I've done here is I've put the sums across the horizontal on a bar graph, and then I've plotted on the vertical, the size of the bar is the percentage of the time things showed up. And let's answer some questions about the different sums you can get on a pair of dice. Okay, so let's look back at the chance of getting snake eyes. Snake eyes is a sum of 2. You got a 1 and a 1. So that's just about 3%. Happens about 3% of the time. We'll take a closer look at this in the homework for sure. Okay, let's do a few more sums. Let's look at a sum of 7. 7 is a very, very important sum in games like craps and also other dice games. According to our data, 7 happens about 17% of the time. There you go. How about a sum of 8? Sum of 8, a little bit less than 7, 14% versus 17%, but a lot more than 2. Matter of fact, there's a really neat looking pattern kind of going up and then coming down here. That's really, really kind of cool. Let's look at one more. Oh, Ate the Hard Way. Yes, I forgot I put this on here. I think I put this on here because I had just watched an old episode of Friends with Jen, and it was the one where Monica and Chandler are in the casino, and Ate the Hard Way shows up. And you know what? Let's not look at this right now. I think this video has gone on long enough, and I'll put this in your homework. I'll have you do some research as to what Ate the Hard Way is and how you can figure out the chance of it. But I think that's a pretty good place to stop for today, and I think we got the big point across anyway. Probability is nothing more than the percent of time an event happens. We'll definitely take it farther tomorrow, but that's good enough for now. Let's try some homework.